Dear students, in this short tutorial we will talk about Lambert Law, which is the foundation of spectroscopic studies, especially when we are talking about the absorption spectroscopy like UV visible spectroscopy. We have already defined the basic terms like absorbance and transmittance, and according to this law, the absorbance is directly related or proportional to the concentration of the analyte in a given sample. And this statement is given by Beers, and another statement that is given by Lambert is that the absorbance is also directly proportional to path length. Say for example, we have a sample here in the sample holder, and from a source of radiations we are following an intensity of like visible or IR radiations on the sample, and some of them are transmitted. So these are transmitted radiations by which the transmittance is calculated, and these are the incident radiations, their intensity, and part of that is absorbed by the sample, which is calculated by means of. So the number of species present in this sample holder, like atoms or ions or molecules of analyte, they will absorb photons, and the absorbance will be directly related to concentration. Higher the concentration of the analyte, higher will be the absorption of incoming radiations. So it means that we measure the concentration of analyte here by measuring the absorbance of electromagnetic radiations, and the concentration is directly related to absorbance. Higher the concentration, higher will be absorbance. And second parameter according to Lambert, that is the path length. What is path length? We can say that the path where electromagnetic radiations they interact with the analyte. For example, if we have a sample holder, so this area between the walls of sample holder, it contains analyte, and the path length is the length of this path through which these radiations will interact with the analyte species. Say if we have a container which is relatively larger in size, so we'll have a longer path length, and a longer path length means there will be more number of analyte particles coming in the path of electromagnetic light beam. So there will be more absorbance, hence we can say that the absorbance is directly related to path length. That is given by Lambert. If we fix the path length, for example, in most of the spectrophotometers we fix the path length to unity, like 1 centimeter width. So in that case there will be only the one parameter, that is concentration, that will result in a value of absorbance. And in that very case we will say that if we have a like graph where the concentration is plotted at x-axis and the absorbance is plotted at y-axis, then this linear relationship means that we will have a straight line like this. provided that the path length is fixed. That is, we say that 1 centimeter. Two relationships together, we can say that absorbance is directly proportional to concentration, and it is also directly proportional to path. And if this proportionality is replaced by a constant, say epsilon, then this equation becomes like this, that A equals epsilon CL. This constant will depend on the nature of the analyte. For example, if your analyte is like acetone, epsilon value will be, say, X. If your analyte is some dye, the epsilon value will be another value like Y, which means that this epsilon is characteristic of the analyte, and each analyte has its characteristic epsilon value. Mathematically speaking, that A when divided by CL is equal to epsilon. The epsilon is equal to A over CL. So A is absorbance, C is concentration, and L is path length. So epsilon value can also be defined as that it is the absorbance of a solution whose concentration is unity, like 1 mole per liter, and its path length is also unity. So accordingly, the units for epsilon will be according to the units of concentration and path length. Absorption. Lambert Law tells us that the concentration of an analyte in a sample and its absorbance are directly related to each other, and there must be a linear relationship between the two in order to have an accurate quantitative analysis. This graph, which we obtain to validate Lambert's law, is commonly referred to as calibration curve, and this calibration curve is necessary to have an accurate analysis. That it is actually a validation of Lambert's law, that if this line is straight, which means that as we increase the concentration, the absorbance also increases linearly.